Hi everyone, my name is Rafaela Gsponer. I'm a second year PhD student at the Institute of Cosmology and Gravitation, and I will tell you about my latest project about tachyonic instability priors for dark energy, where we try to answer the question if we can use additional theoretical information to speed up cosmological parameter search. So let me just go into the motivation of the work. As we all know, general relativity is our standard theory of gravity, and it's a beautiful, unique theory, which is kind of nicely summarized in the Lovelock theorem, which state that gravity at general relativity is the only second-order local theory of gravity with just a metric tensor in 4 dimensions. So if we actually want to go beyond GR, we kind of have to break one of these assumptions of the Lovelock theorem. Either we add new field content, or we assume higher dimension, or we take into account second order or higher derivatives of the equations of motions, or look at non-local theories. In the project I was looking at, we were looking at Horndeski scalar tensor theories, which are like the most general set of theories still in 4 dimensions and with second order equations of motions. But besides the metric tensor, there's an additional scalar degree of freedom. In 2014, a paper nicely showed how you actually can split linear perturbations, or like perturb the action of Horndeski scalar tensor theory around a Fn or FRW background, and kind of split nicely the background and its linear perturbation, where we can keep track of the background solution simply by looking at the Hubble parameter and describing our dark energy model by just 4 parameters. These so-called alpha parameters are really nice because they have a physical intuition to it. So we looking at alpha k, which describes the kinetic term of this extra scalar field, alpha b, which describes the mixing between the scalar and the tensor, alpha m, which describes the effective Planck mass, which no longer has to be a constant in these dark energy models, and alpha t, which describes the speed of gravitational waves. In the work I was looking at, we actually concentrated on a subset of these Horndeski theories. We set alpha k to a fiducial value because it's from the data we have nowadays, it's actually quite hard to measure, as well as we used the recent gravitational wave constraints and assumed that the gravitational wave move at the speed of light. So alpha t is in this case equals to 0. So we end up with alpha b and alpha m, which describes our dark energy models. And what we now would like to do is actually test our theoretical model to data. In order to do this, we need to choose a parameterization for these alpha parameters, where we stick to a parameterization which is proportional to the energy density of dark energy. Like this, we just enforce that these alpha parameters will become important at late times. And then we run MCMC chains where, like, for each initial condition, like in this parameter space, initial conditions, and therefore like slightly different dark energy model, we compare our how the universe would look like in this model to the data we actually observe. And in the end, we find something like this. We actually get contour plots, which describes how likely we observe a universe with the data we measure from CMB and galaxy clustering data according to alpha M and alpha B. This is actually a computational, quite expensive task to do. So what we actually would like to do is use additional theoretical information to speed this up. So in my work, what I was looking at is one kind of these theoretical priors, the so-called stability criterions, because we know that since we do perturbation theory, we know that the perturbation have to be remain small. So if we go through this parameter search and move to an area in the parameter space where the background becomes unstable to perturbation, we know that would not be a feasible action and the parameter space there could be excluded. And in general, there are like 3 instability conditions which we can identify. First one would be the ghost instability, which corresponds to a kinetic negative energy. the gradient instability, which corresponds to that the sound speed squared is negative, and it leads to an exponential destabilization of the background. And the third one would be the tachyonic instability, which corresponds to a negative mass squared of the field. So we can then implement these ghost and gradient priors in Einstein-Boltzmann solvers to actually speed up the MCMC change. And this has been done for ghost and gradient priors before. On the right-hand side, you see a plot from the contrast plot we saw before, with the prior for the ghost and gradient enforced and without. And you actually can see that the contours are nicely reproduced. But the advantage of actually implying such priors is that now on the right-hand side, you see this dark red area, which actually corresponds to a region where ghost and gradient instabilities are identified. So at the beginning, we actually tell our CMC run that this parameter space doesn't need to be looked at, and it actually can spend more time looking at the other regions of the parameter space. In my work, I wanted to complete this set of instability conditions by including the tachyonic prior. With the tachyonic prior, it's a little bit different to ghost and gradient because it is not as clear-cut as the other two, because as soon as we have kinetic negative energy, we know something is going wrong, as well as with the sound speed. For the tachyonic prior, we actually have a general relativity equivalent, which would be the gene's mass instability. So we know that there, in order to gravitational collapse to happen, there has to be a tachyonic instability. Now the question is, can we identify a prior which actually tells us if instability can be kept under control or not? In order to do so, we were looking at the gene's mass instability. And the gene's mass instability normally evolves in the scale of the Hubble scale. We therefore introduced this dimensionless parameter gamma, which tells us the size of our tachyonic instability compared to its GR equivalent. We then run 3 different chains. One where we put prior in place where we had this really hard cutoff and just allowed for instability of the size of GR. And we can see on this plot here that not the whole parameter space is actually resolved. There's like this part here, which corresponds to this orange shade region here, where the code identifies tachyonic instabilities. But this is wrong because the contours itself would tell us that this parameter space here would be feasible. So we had to go to a higher prior and actually allowed for instabilities which are 10 times the one of GR. And again, we found that not all of the parameter space could resolve, and there's still a slit here where tachyonic instabilities were classified as bad, although the data tells us it can keep it as a viable theory. In a last step, we actually had to go up to a cutoff scale of 100 times the GR instability to allow and recover the whole parameter space. But as you can see from this plot, there was no additional speed up in implying this prior. So the conclusion of my work was actually that we caution against using tachyonic priors because they are very involved. And a lot of literature before this work implied a very harsh cutoff scale of equals to 1, which then would actually cut up a very big region of your parameter space, which would be perfectly viable from the data side view, and therefore bias your results in an area where the CMC actually would look at. And that's kind of the conclusion of my work. If there are any questions, I'm happy to answer them.
Cool. Okay, thank you very much. So you're arguing against tachyonic priors. You already have a couple of other priors put in. Are there any more on your list to consider now?
No, I mean, these are like priors which kind of targeting the speed of CMC chains. There are other priors which actually kind of add additional information like orthogonal to the data, which like kind of comes into from a new side, for example, like positivity bounds and how like particle scatters. So you could come from the particle theory side and include new priors. But just for the speed up, this set with the tachyonic instability would now be complete.
Cool. Okay. And in terms of speeding things up, can you give us an idea of how long one of these MCMCs currently takes?
These are quite expensive. As far as I remember, they were run on 128 knots for 2 weeks. And with actually implying this price, in the end, we gained a speed up, but in the end, we were biasing our results in the wrong area of the parameter space. So although we saw a speed up, in the end, we had to go back.
Cool.